Hi, my name is Sean Curtin, and for my differential equations project, I modeled the motion of a Formula One car accelerating through a resisting medium. I chose this topic because I've always been interested in racing physics, and F1 cars provide a perfect real-world example of how differential equations govern motion under complex forces. This project meets all the requirements because it's based on a first-order nonlinear differential equation from section 4.3 and uses real Formula One telemetry data to compare a mathematical model with an actual physical system. To make the project clear and easy to follow, I included several visual aids. First, I show a force diagram of the car, including engine force, aerodynamic drag, and rolling resistance. Next, I present MATLAB plots generated with ODE 45 that display the car's velocity over time as the equation is solved numerically. Finally, I include a side-by-side comparison of my simulated acceleration curve with the real telemetry from Max Verstappen driving at Silverstone. These visuals help connect the mathematical model directly to real racing data. My project models how an F1 car accelerates from low speed to high speed while working against drag, which increases with the square of velocity and rolling resistance. Using Newton's second law, I converted the net force on the car into a differential equation describing velocity as a function of time. I then solved this equation numerically with the ODE 45 tool to generate a complete acceleration profile. The goal was to determine whether a simplified physics model using only engine power, drag, and rolling resistance could realistically predict the performance of an F1 car. When I compared the results to the real telemetry of the Red Bull RB20, my model was accurate within 4%. This showed that even a simplified differential equation can capture the essential behavior of a very complex engineering system. This project changed how I view differential equations. Instead of being purely abstract, they became a practical tool for predicting real-world engineering performance. I also learned how valuable numerical solvers like ODE 45 are when dealing with nonlinear systems that don't have simple closed-form solutions. Working with actual telemetry data gave me experience with model validation, an important part of engineering analysis. Overall, I learned that the same equations we study in class can accurately describe high-performance systems like a Formula One car, and that differential equations play a central role in understanding motion when forces are involved.